Evening, Dr. Tran.
Oh,
Hi.
hey, Chris, what's up?
I'm saying hi.
Yep. Sorry, say again, Chris?
I said I'm saying hi. Hi,
Oh,
Dr.
hi. Hi, Chris. Sorry, the volume was a little bit low, so I could hear you talking, but I couldn't quite hear what you were saying. Yeah.
Okay. Sorry about that.
Oh, no worries. No, that was my fault.
Dr. Tran.
Hello.
It's me, Chris, again.
Hey, Chris.
Yeah, I have a question about activity 2.
Sure.
So in problem 3, question 3, if the bike crank were to fail, where would you expect it to fail? And what would the mechanism of failure be? What do you mean by mechanism of failure?
So mechanism of the failure would be kind of what's causing the stress
Okay.
in that part. So in that particular case,
It would be compression or tensile?
in that case, it would be tensile, right? So
Okay.
it'd be because of the bending stress, you have one part that's being kind of basically ripped open. Yeah.
So the compression strength is higher than the tensile strength, is what you're saying.
Yes, and so yeah, and so the compressive stress is not as high as the tensile stress.
Okay.
Mhm.
I was a little confused about when you asked for the mechanism of failure. I was thinking like, what do you mean? Like, is it cyclic failure or
I see.
is
Yeah,
it
yeah.
like creep or I was a little thrown off there.
Oh, yeah. In this case, it's just just tensile failure basically. Yeah.
Okay. Thank you.
Mhm. All right, it's 7 o'clock. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Doing good. Oh, there's like 200 people in the class. All right, more people are coming. Okay. All right. So today, today's Wednesday, and so today we're going to be covering material properties. So actually, the timing is actually good. So last time I taught this class, I taught it in a fall semester where we had a Monday holiday kind of before activity 3. So it was a little bit awkward because we did kind of this material properties after activity 3, but the timing is better here because we'll finish all these kind of really basic lectures before activity 3, which is also the conclusion of kind of the really basic kind of ANSYS stuff, right? So let me mention this before I forget. So remember, Monday is a holiday, so we're not going to have class on Monday, but I will have my regular office hours on Monday, and so we're not going to have an activity open at that time because I think this activity is due this Friday. But if you want to come by, if you have questions, just in general. If you want to get a preview of activity 3, I'll probably have it posted by Monday just so you can take a look. Then you can stop by then as well. But we're not going to have a lecture on Monday, and I'm probably not going to come to campus on Monday too. So Monday office hours will just be on Zoom. Okay. Okay. All right. And so that's it for my announcements. Are there any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. And so the topic for today is material properties. Okay. All right, so we've done meshing, we've done boundary conditions. And so I would say kind of the last kind of basic topic for practical FEA is talking about material properties, right? So some of today will be review. So we kind of already talked a bit about this when we did our review of mechanics, but I think it's kind of worth repeating a little bit of that just so that we can talk about a bit more interesting topics of material properties, things like plasticity, things like anisotropic materials and hyperelasticity. Okay, so today, a little bit of today will be a review of the review, and so it'll be kind of this maybe the 4th or 5th time you've seen this overall in your life. But I think it's important to kind of be complete with this so that we can build on that for other stuff. Okay. Okay, so what do I mean by material properties? So material properties, this is kind of a general term for basically all the physical parameters of a material that will affect how it responds to any kind of physical stimulus. Okay. Okay. So every material has a ton of properties that's associated with it. Right? So you're familiar with probably the vast majority of these properties that are at least relevant for engineering. So these are things that would be like the Young's modulus, Poisson's ratio. We've already seen that in activity 2, and we've seen kind of how that makes an effect. But there's also things like the density of the material that's going to be relevant in activity 3. And even non-structural properties as well. So there are thermal properties, there are fluid properties, there's electromagnetic properties, things like thermal conductivity, melting point, thermal capacity, conductivity for electromagnetism. So there's a ton of properties, right? And so whenever you're doing any kind of practical FEA that uses these real materials, it's of course, it's going to be really important to make sure that you get all these properties correct. Okay. All right, so that's kind of the physical definition of what material properties are. That's probably kind of how we understand them already. But specifically for FEA, there's also kind of a mathematical reason as well. Okay, Because remember, FEA, essentially what the FEA is doing is that it's solving all of the governing equations underneath the hood, right? So you have all these very complicated partial differential equations. And the way these equations are structured, the material properties kind of act as kind of coefficients in these equations. And so, of course, depending on the values of these parameters, they're going to modulate the solution kind of one way or another. Okay. All right. And so, today we're not going to take a careful look into all of these equations, but it's kind of important to know that underneath the hood what these properties are doing, and so they're basically entering the equations in some way. Okay. And so a lot of times, for most practical FEA, the material properties is not something you're going to give a lot of thought to, because a lot of times, especially if you're using like a commercial version of ANSYS with a much more sophisticated material library, a lot of times you're just going to be selecting material from the library, okay? And then you're going to select it, you're going to trust that it has the properties that you need, and then you're just not really going to think about it again. Okay. And that's kind of why I save it to last, because it's usually the part of FEA that you give the least amount of thought to. Okay? But with that said, there is still a lot of complexity in the material, and especially if you're working for a company that's using maybe its own homebrew material, or maybe like a modified version of the material, right? Knowing what goes into the material models and how you can modify them is an important skill. Okay? And so there can be So today, you'll hear me use the term material model a lot, okay? Because the reality of material properties is that, it may seem, I think when, especially, I think especially for my undergrad student, material properties is something that they kind of, what they interpret is that, you kind of look up the properties in the table and you just kind of plug those into the equations as needed, okay? The reality of material science is that, we're actually not that far in terms of having very accurate material models, right? So the equations that we have, they have a lot of limitations, and so a lot of times if you're expecting to have very interesting deformations, or maybe you have a complex material, you have to actually give a decent amount of thought in terms of how the material model is mathematically formulated, and whether that's actually appropriate for the application that you want. Okay. And so today, we'll talk about some of the more common material models. We've already done quite a few. We've seen a few already in our activities, and we'll go from there. Question. So what does nuance mean? It's nuance. I use that term. Maybe I'm not using it correctly. I just like saying the word. But nuance is basically something that you may not have thought about before. So it's kind of like a hidden complexity in terms of how you think about it. Yeah. Mm-hmm. All right. Any other questions on this? Okay. All right. So let's go over some of the more common material models and kind of how they work. All right. So the first one is going to be review. So we've already talked about this in the class, but it's kind of worth repeating. The most common material model that you'll see in practice, because it's the simplest, is linear elasticity. Okay. And so linear elasticity, this is a material model that assumes that the relationship between stress and strain in the material is purely linear. So we have the very famous Hooke's law, where stress is equal to the Young's modulus multiplied by the strain. Okay, and so what that yields is a graph that looks like this. Okay. On the horizontal axis, we have strain, and on the vertical axis, we have stress. And then the slope of this line is E, which is the Young's modulus. Okay. All right. So linear elasticity, very popular because of its simplicity. And so you really only need to define two parameters here. Okay, so the first, of course, is the Young's modulus. So usually this is given the symbol big E. Okay. All right, so I'm not gonna go through, we've already kind of talked about the definition of Young's modulus, but basically this Young's modulus tells you how stiff or how strong the material is, right? So the higher the Young's modulus, the stronger the material. Okay. All right, so that's a Young's modulus. Number two, the one that we have to do, and this is strictly a multi-dimensional effect, is the Poisson's ratio. And usually we get that the symbol mu. Okay. All right, and so this is also something that we've defined before, and so I'm not going to go through this in detail again, but basically the Poisson's ratio tells you how much the material will deform in directions perpendicular to the loading direction. And I believe, when we did our review of strength of material, we also talked about the shear modulus. And so that's a thing as well. But usually, you don't really define that one. And so once you define the Young's modulus and once you define the Poisson's ratio, then the shear modulus is computed kind of automatically from those properties. Okay. All right. And so in this form, linear elasticity is what we call an isotropic material. Okay. So in activity 2, you might have noticed that term isotropic come up. Okay. And so what isotropic basically means is that the strength of the material is the same in all three directions, or I guess in all directions. And so if we were to have a cube here, okay, as an example, let me draw 3 cubes. It's not bad. They're supposed to be all the same, but of course, my bad drawings go some are bigger than the others. But imagine they're all the same. Okay. All right. So for an isotropic material, if you were to load these cubes in 3 different directions, so let's say that we applied a force like this. Okay. We have the same force P from top and bottom. If we apply the same force P going from left to right, and then maybe the same force P going into and out of the page, like that. Okay. And so if we assume this loading is the same magnitude in all directions, but just the only thing that's different is the direction. Okay. If our material is isotropic, then all 3 of these situations are going to have the same magnitude of deformation. Question in the chat. So is a property like density independent of the Young's modulus of Poisson's ratio, or can it be derived from those two? Density is mostly independent. We a lot of times mathematically we define it as independent. I don't believe there's an equation that relates the two. If you're talking about kind of on a molecular basis, I think those two are generally related, and intuitively you think so too. So, generally if a material has a very high density, what we assume basically is that there's a large, the molecules of that material are very densely packed together, right? And generally speaking, the more densely packed the molecules are, the more strongly they can resist deformations as well, right? So there's a correlation. And so, generally the materials that are more dense also have a higher Young's modulus. But mathematically, I don't believe there's a relationship between them. Mm-hmm. Yeah. The reason I'm not talking about density here is that density, at least in static FEA or static simulations, which is what we're doing, the density is really only used to compute weight. So the density by itself doesn't actually contribute to any kind of strength of the material, but it does contribute to the weight, which we'll see in activity 3. Yeah. Mm-hmm. Okay. All right. So that's for an isotropic material, and so isotropic materials are pretty common in engineering. So a lot of very common engineering materials are isotropic. Okay. And so generally speaking, most metals are isotropic. And the reason for this is that if you look at the molecular structure as well, metals are known for having a very uniform, very kind of organized molecular structure. And so because of that, there's no kind of weird directionality in metals. And so generally speaking, metals are pretty isotropic. Okay. So that's good. And in fact, the first 2 activities that we've done, if you kind of notice, we've used metals. And so for the first activity, we did steel. For the second activity, we did aluminum, both of which are isotropic, which is why we could define them as kind of a simple kind of 2-parameter system. Okay. But at the same time, there's a lot of materials that we like to use in engineering that are not isotropic. So I'll give a couple examples here. And so the first one that kind of comes to mind is any kind of wood material. Okay. So wood comes from a tree, right? And the thing about trees is that they have kind of these natural fibers that kind of run through the tree, right? And so, before the tree was chopped down, these fibers are how, nutrients and water kind of transports through the tree, okay? So when you're doing any kind of engineering design with wood, you need to be aware of kind of which direction the fibers are going. Okay? And so usually, for most woods, the fiber direction is usually the strongest direction for the piece of wood. Okay, so the wood is going to be strongest in that direction. Okay. That's a very common one. Another common one that you'll see, especially nowadays, are composite materials. Okay, so composite materials are, of course, materials that are kind of blended or they're kind of created to fit a certain purpose. And usually, these materials are designed in a way such that they have more strength or less strength in a given direction based on their application. Okay? So I'll give one more example. There's certainly more examples out there, but this is kind of an example kind of based on a lot of the work that I've done before, which is becoming more and more prevalent nowadays, which is biological materials. Okay. We're talking about like human tissue, animal tissue, things like that. Okay. And so these also have very strange material properties. They're definitely not isotropic. Part of that is due to, very similar to wood, a lot of biological materials have a certain kind of, either fibers or sheets or just kind of the way it's kind of molecularly organized. And so, there's certain directions that are often stronger than others. Okay? In particular, one thing, especially for human tissue, so that's the one I kind of have the most experience with. A lot of human tissue has a lot of water associated with it, right? And so you start to enter this this area called viscoelasticity, where your material kind of behaves somewhere in between like an elastic solid and a fluid, and so that's when things get kind of really crazy. Okay, we're not going to go through viscoelasticity because that's kind of a whole class in itself, but that's kind of where it's coming from. Okay? All right. And so, when you
Dr. Chan, I have a question.
Oh, sure, yes.
What about 3D printed materials? Do you know what category they would fall into?
Yeah. So 3D printing materials, they're also kind of composite materials, like someone mentioned in the class. 3D printing also has the kind of the interesting factor where like a lot of 3D printing is kind of built in layers. And so usually the layer direction is usually the weakest active direction because you're kind of relying on kind of the layer by layer stickiness to give you strength. And so that's also something that's a factor. So yeah. And there's also things like carbon fiber, very popular in aerospace, that has its own material properties because that's kind of layered in sheets as well. And so yeah, so 3D printing, there's a lot of different examples of properties that are not isotropic. Yeah. All right. And so in ANSYS, there are methods for you to implement these non-isotropic materials. So I'll give you kind of two examples, two of the more common ones that I usually see. So there's a lot more in ANSYS, and so there's certainly a lot more you can do with non-isotropic. But I'd say these are, especially the first one, I'd say, it's kind of the most common. Okay. All right, so the most common one, because it's not too crazy, it's called orthotropic elasticity. Okay. All right, so orthotropic elasticity lets you kind of implement this idea that you have strength in different directions. Okay, and so to have an orthotropic material, you need to specify 9 material parameters. Basically, each of those 9 parameters, what they represent are the Young's moduli in each of the 3 directions. Okay. The Poisson's ratios in each of the 3 planes. And the last thing you need to specify that's unique in this one, so we didn't have to do this in isotropic, is you actually need to specify the shear moduli in each direction as well. So 9 parameters is a lot, right? And so, if you compare this to our isotropic linear elasticity, which we only need 2 parameters, 9 is usually a lot more. Okay. And what you'll find out is, and what you'll see, most common is that once you start to get to more complex materials, it gets harder and harder to kind of look up these properties online. Okay. And so if you're lucky, and if you're using kind of a commercial version of ANSYS that has these materials built in, that have all these constants defined already, then that's great. But if you're going to be trying to define one of these materials from scratch, create a custom one, that could be a little bit difficult unless you work for a company that kind of maintains their own database internally. Okay, so I would say that's kind of the more common form. Because I've tried to look up kind of material properties like orthotropic parameters online, and it's hard to find reliable sources, and it's hard to find kind of consistent data. And so, just kind of be aware of that if you're using these material models. All right, and so that's orthotropic elasticity. And so the other type of elasticity that you can use is called anisotropic elasticity. And so anisotropic elasticity is probably the most general material model that you can use. Okay? Because with isotropic elasticity, generally what we can say is that we're making a lot of assumptions in terms of how the material behaves in different directions. Even with orthotropic elasticity, we're still kind of making a lot of assumptions in terms of how the kind of the stresses and the strains kind of relate to each other. Okay. For anisotropic elasticity, we make no assumptions at all. And so this is the most general linear elastic material model. Okay. Any guesses on how many parameters that anisotropic needs? So if isotropic needed 2 and orthotropic needed 9, anisotropic, which kind of gets rid of all of the assumptions, it requires 27 parameters to be specified. So obviously, 27 is a ton of parameters. And so, for most practical purposes, you're not going to be using this unless you really kind of know what you're doing. Okay? But the reason I bring this up is that, I want to kind of show you that ANSYS does have a lot of these kind of material models. And sometimes you do have access to this kind of data. And so if you're working for a company that's using some kind of very weird, like composite or biological material, and it has a very kind of complex material model, ANSYS has the capabilities to model it, given you can specify all these parameters. But if you're working with a company that specializes in these things, usually they have these parameters. But for proprietary purposes, they usually don't like sharing them with the world. Okay. All right. And so, anisotropic, very rare. I would say probably the most common case that you would see it is in, like, again, if you're working for a company that kind of develop its own materials, or some biological materials can do this as well. And so, if you wanted to, kind of get around that viscoelasticity thing we were talking about earlier, using anisotropic elasticity usually gets you somewhat close to that behavior. Okay, if you select the parameter properly. Okay. Any questions on this so far? Okay, so that's linear elasticity. Okay, so even though we went through isotropic, orthotropic, and isotropic, that's still technically all linear elasticity. Let's talk about kind of the next level, okay, which is plasticity. Okay. So usually, when you're first starting out a structural simulation, linear elasticity is not a bad place to start. So it's even if you're using a composite material, linear elasticity is not bad. Okay, because even for the most complex materials, as long as your deformations are relatively small, most materials exhibit kind of linear behavior for small deformations. Okay. Okay. The operative word there, of course, is small, and so that kind of begs the question of how do you define small deformations? Well, it's a little bit different for every application, and it depends on how non-linear your material is, right? If you're working with a fairly kind of standard metal, you can probably get away with fairly larger deformations and still assume that linear elasticity is still going to hold. But if you're working with like a composite material, maybe you don't want the deformation to exceed, I don't know, like 2 or 3% of the overall length of the structure. Okay, but if you're in a situation where the deformation is going to be very small, maybe less than 1% of a dimension of your material, I would say just don't even worry about it. Just use a linear model. I think it's going to be fine. Okay, but of course there are situations where you are going to have larger deformations. Okay, and that's when you start to get into kind of plastic behavior. Right. So probably, everyone's probably somewhat familiar with plastic behavior. Okay? And so visually, the way we know plastic behavior is occurring is because the stress-strain relationship kind of breaks away from that linear trend. Okay? right, so our typical stress strain curve. Let's go ahead and draw it again. Right, so most materials will have a linear region where stress and strain are kind of have this linear relationship. But usually once you get past a certain point, and this point right here is called the elastic limit. This linear relationship starts to break down. And so what you're going to have is kind of more strain or, not as much stress. Okay? So it kind of starts to flatten out kind of like this. So I believe, I think we discussed this as well when we did our strength of materials review, but this is what we call plastic deformation. So I did it a little bit extreme there. So usually it's not that flat. And so, usually there's still some slope to it. But I didn't give myself enough room to draw this curve. So, it ended up being pretty flat. Okay. So what's unique about plastic deformation? So if you're within the linear limit, right? And so let's say that, you apply a load to your material and it strains to a certain point and it stays within this kind of linear zone. The assumption is that if you release the load, then the material will go right back to its kind of original resting position. Okay. But if you exceed that elastic limit, and so you apply a stress that's kind of, that pushes the stress above the elastic limit, then the deformations that you're going to be exhibiting or observing, some of that is going to be permanent. Okay. And so what happens is that if you kind of push past this elastic limit, and so let's say that you push into this plastic region right here, okay, and then let's say that you release the load, okay, it's never going to reach a point here where you have zero strain again. So it's going to come straight down, okay, or it's going to be like that. And so once you kind of get past that elastic limit, then basically there's always going to be some strain there because that's kind of permanent plastic strain. And so, of course, this curve that we have here is in 1D, right? And so in 3D, the stress strain relationship is a bit more complex because you have strain in kind of all three directions. Okay? And so that kind of begs the question of, how do you know when you reach the elastic limit in 3D? So in 3D, what we use to compute, to compare to the elastic limit is the von Mises stress, so the equivalent stress. And so the equivalent stress, the von Mises stress, we went over that. We did our strength and materials review, so I'm not going to write it again. But just know that that's what it's used for. Okay. One of the other things that it's used for. Okay. And so now, the next thing that we want to discuss here is, how do we actually implement a plastic material in ANSYS? And so ANSYS can do plastic deformations as well. Otherwise, we wouldn't be talking about it. But of course, if you want ANSYS to take, to take plastic deformation into account, you're going to have to add some additional parameters, some additional properties to your material. All right, so the first thing that you need to specify in ANSYS is the shape of the plastic deformation region. So this is probably the most important thing that you want ANSYS to account for, okay? Because once you get past that elastic limit, you know, you're gonna be seeing that the strain is going to start accelerating a lot more rapidly with increasing load, okay? And so you want to make sure you capture that behavior as well as possible. Okay, so you have a couple options for this, depending on how much data that you have. You know, a lot of material models, a lot of it just depends on how much data that you have available to you. And so the first option, which is the simplest one, is called the bilinear stress strain curve. And so for a bilinear stress strain curve, basically all you do is you specify a second slope, okay? Because we know that in the linear region, the slope of the stress strain curve is going to follow the Young's modulus. And so for bilinear, you're just going to define a second slope for the plastic region. Okay? So it looks just like this. Okay. So we have strain, stress. And so we have the initial linear region, okay, where the slope of this line is the Young's modulus. Okay. Okay. And so for the bilinear model, basically once you reach the elastic limit, then the slope of this curve is going to change. So it's going to start to look like this instead, okay? Where this right here, this is the new slope. And that's something that you have to input. So you have to input what that new slope is going to be inside ANSYS.
So it's going to be linear?
Yeah, for this one, it's always going to be linear. So of course, this is a more crude model because usually the plastic region there's curvature in there. But if you want kind of the simplest one, just with the least amount of parameters, this is kind of the one. Yeah, so that's the main benefit for this one. So for the bilinear one, you only have to specify just one additional parameter. And so how you choose that new slope, you know, some materials in ANSYS might already have this bilinear model, so that's already defined. But if you want to define the slope, you know, you're probably just going to take an average of the slope of the plastic deformation region. Okay. All right. So that's one option. Or the other option is called multilinear. And so multilinear stress strain is kind of the preferable option if you have more data available to you. Okay. So for multilinear, just kind of like the name implies, you can define the excuse me. You can define the plastic deformation region as a series of smaller linear lines. So let me go ahead and draw it out. And so of course you would have your initial linear region. And so this would be the Young's modulus. Okay. Then past a certain point, you would reach the elastic limit. And then from here, it almost kind of looks like almost like an Excel data sheet. And so you would have basically, you would kind of define these data points. It's like this. Okay. These points here, each of these points are basically individual stress strain data that you would input manually. Okay. So in activity 2, actually, someone asked about this, not with regards to plasticity, but I think they noticed on the right-hand side there was like a data table in terms of, you can define something like the Young's modulus and how it varies with temperature. Okay, so that's kind of the format that ANSYS uses for a lot of these things. And so if you have kind of data available to you, you can input that into the table just like that. And so this is something very similar. And so for the multilinear stress strain, you would input into the data table specific points of stress and strain in the plastic region that you may know about. Okay. And once again, this is something that, I would say normally is very difficult to find online, unless there's a published scientific paper on the material properties. They may have this data, but a lot of times this is data that companies have internally for the materials that they have. Okay. And so for this class, we're not, just because of the kind of the limitations of the software that we're using and the limitations of the material models, I don't have any planned examples of this, but I did want to make you aware of it so that, if you are planning on using ANSYS for your company, just ask around. And so if you ask around, someone probably has the material data sheet or the material kind of file, which has this data. Okay. But if you're kind of operating outside of that, then usually this data is kind of hard to come by. Any questions on this? Okay. All right, so that's one thing that you have to specify for plastic deformation. Okay, so you have to specify the shape of the plastic deformation region. The other thing you have to specify to use plasticity in ANSYS is the hardening rules. Okay. So one other thing that happens once you kind of exceed that elastic limit is that the material itself starts to harden a bit. Okay, or in other words, the tensile strength and the compressive strength tend to increase once the elastic limit is hit. Okay. But there's different ways for the material to harden as well. And so one thing you have to specify in ANSYS is kind of what's called the hardening rules. Okay? Right. And so I would say that, both of these hardening rules are kind of extremes. And so for most materials, the way that they harden is going to be somewhere in between these two extremes. And so when you pick one, pick one that kind of more closely resembles your material that you think is going to happen. Okay. All right. So the first option that you have is called kinematic hardening. And so in kinematic hardening, what it assumes that the difference between the tensile strength and the compressive strength stays the same. So basically with kinematic hardening, if one of those gets stronger, and so let's say the compressive strength gets stronger through the hardening process, that means the tensile strength is getting weaker because the difference between the two is always going to be the same. Okay. So typically, for compressive strength, we model that as kind of a negative number because negative stress is often we model as we model compressive stress as a negative. Okay. And tensile strengths are positive. Okay. And so with kinematic hardening, it's kind of like the difference between the two is still the same. So if one goes up, the other one kind of goes down. Okay. All right, that's one option you have. The other type of hardening that you have is called isotropic hardening. And so what isotropic hardening assumes is that, both the tensile strength and the compressive strength are going to have the same magnitude. And so if one gets stronger, the other gets stronger by the exact same amount. All right, so I would say for most materials, I would say kinematic hardening is probably closer to what they do. Because if you can imagine, you're stretching material and it kind of starts to kind of have plastic deformation. Usually, either the compressive or the tensile strength is probably going to start weakening. So I would say kinematic hardening is probably closer to reality for most materials. But isotropic hardening is there for if you have some kind of composite material that has that behavior. Okay. Right. All right. Any questions on this? Okay. Okay. So that just about covers linear elasticity. So actually everything that we've been covering so far is for linear elasticity, right? So the whole kind of theory behind linear elasticity is based around the fact that you have stress and you have strain in your material, and they're related up to a constant. So you have a Young's modulus that basically relates the stress and strain. Okay, and so I would say there's a ton of theory behind linear elasticity. I think it's what's taught in most classes on structural mechanics or strength of materials, and so I'd say most people are fairly familiar with linear elasticity. Okay? But over time, what people have discovered is that once you kind of get outside that small deformation region, not all materials kind of follow this kind of plastic behavior. So this plastic behavior, it works for some materials. But for other materials, you have kind of more complex relationships between stress and strain that can't really be modeled with a linear line and a plastic region. Okay. And this kind of came about, once people started experimenting with composite materials and more complex stuff. They started measuring things like biological materials and stuff like that. Okay. And so there's a whole other school of thought in terms of how you can define material properties. And I'll kind of just group a lot of them into one. We'll call it hyperelasticity. The naming is not the best because when you think hyperelasticity, you think that these are materials that are super elastic, right? So you think of things like rubber bands or things like that. So it's not that. So you could have some hyperelastic materials or some hyperelastic material models that actually model something very stiff. Okay? So hyperelasticity is just kind of another way to think about kind of the relationship between stress and strain within a material. Okay? All right. So the definition for hyperelasticity and the reason it kind of got its name is that it's a more general material model framework that's meant to capture large deformations more accurately. Okay. All right, so the key words in this definition, of course, are large deformations, because that's kind of what it was designed for, so that we can model these more accurately, and some people would argue more elegantly too, so that you're not kind of switching between a linear region and a plastic region, and then in the plastic region you have all these different lines and different curves. And so what people thought is that there's a more elegant way to model this, and it's called hyperelasticity. Okay, but the other key word in this definition is framework. Okay? Which seems kind of a weird kind of line to highlight, but it kind of highlights this pretty well. And so there's not just one hyperelastic model. There's actually hundreds of them. And so there's a lot of hyperelastic models, but they all kind of follow the same idea. Okay. And so instead of using kind of an algebraic equation to model stress and strain, which is essentially what linear elasticity does, the idea with hyperelasticity is that you define what's called a strain energy function. And then what you can do is that you can take derivatives of the strain energy function and kind of fit it into different equations to form your stress strain relationships. Okay? Right. And so the idea with strain energy, it's defined in a way basically with the assumption that every material or every object has a certain amount of potential energy that gets conserved as the object changes into different deformation states. Okay? And so when you add loads to a material, it's almost like you're adding to the potential energy of the system, so that and that's kind of what causes deformation. Okay. So the reason this is more general is because you're able to capture kind of nonlinear stress strain curves a lot more easily. Okay. And it's able to capture different material behavior under tensile and compressive states a lot more easily as well. Okay, so it's more general. The downside is that it also comes with a lot of complexity as well. Okay. So generally requires more data. And so it requires a lot more data and parameters to kind of fully specify. Okay. Right. Not only do you have to specify parameters, but you also have to specify the form of the strain energy function as well. Right. So remember I told you that hyperelasticity is just a framework. And so when you talk about strain energy functions, that kind of assumes that there's just one strain energy function, right? In fact, there are lots of strain energy functions out there. If you even look into ANSYS, I think they have at least a dozen in there that you can use. Okay. And a lot of these strain energy functions, they're named after the researchers that discovered them. Okay. And each of those strain energy functions usually work for certain types of materials. Okay. And so I think, one of the cool things, I guess, about ANSYS is that if you're really kind of a nerd about kind of material properties and material models, ANSYS kind of really gives you a lot of tools that you can really experiment with, which is really cool. Okay. A lot of those tools are fairly redundant. And so, as is the case with kind of such a big software like ANSYS, there's always going to be a lot of redundancy. And so, even if you use ANSYS professionally for 30 years, there's probably going to be parts of ANSYS that you're just never going to touch, and you may not even know what that does. And I think for a lot of people, hyperelasticity is kind of one of those things where, at least in my own experience, what I've seen where I've seen hyperelasticity used the most is mostly in a research setting. So for people that are doing kind of academic or kind of research stuff, they like to use hyperelasticity just because a lot of those researchers are just math nerds and they like to do these kind of things anyway. But it also kind of works with kind of the weirder materials that they use. Okay. And so I wish there was more that I could speak on for hyperelasticity. But it is something that I really only have kind of a surface kind of understanding of. But it is something that I want to make you aware of that's out there. And if you are kind of an expert in material science, this is something that you can experiment on. Okay. And so if you go into ANSYS and you specify that you want to use hyperelasticity, the first thing it's going to ask you is, what form of the strain energy function that you want to use. Okay? And so there's lots of options for that. And then after you choose the form, then it's going to ask you, what are the parameters for the strain energy function. Right? And I think one of the downsides of hyperelasticity is that a lot of times these parameters, they don't really have a strong kind of physical intuition. Okay. Because if you think about linear elasticity, even when we were talking about, like orthotropic elasticity or anisotropic elasticity, a lot of times those parameters have a physical intuition. And so the Young's modulus, you specify that, kind of exactly kind of what you're specifying. For the Poisson's ratio, it's kind of the same thing. So, you kind of know what it is. For these hyperelastic material models, oftentimes you're specifying these parameters, but they might as well just be kind of just alphabet soup of, stuff that you do. And so, maybe you looked up a hyperelastic material model in the literature and they said to use these material parameters and you say, okay, but you may not kind of understand what those parameters are referring to. Okay. And that's kind of the trade-off in general. So generally, if you have more complexity in your material model or just more complexity in your model in general, yes, you can capture kind of more interesting behavior, but then it becomes more difficult to kind of track and see what everything is actually doing. Okay. So it's kind of usually a trade-off. But if you have a hyperelastic material model, you may get kind of an interesting stress-strain relationship. It looks like this. So maybe you get one that looks kind of like that. Okay. And something like that is very common, where maybe in the very kind of smaller regions here, you have kind of a linear region, but it very quickly becomes non-linear. So if you have a material that behaves like this, you probably want to consider using a hyperelastic material model. Okay. All right. Any questions on hyperelasticity? Okay. All right. And so that about wraps up this lecture. And so, in summary, there's a lot of depth and there's a lot of complexity to the material models. But again, for most people, I think you're not going to see a lot of this depth unless you're a material scientist or unless you're using kind of a weird material. But it's useful to know kind of the tools that are available, so that when if you do end up using one of those kind of composite materials, if you're simulating something like 3D printing, you kind of know the tools available to make sure that you can make your simulation as accurate as possible. Okay. All right, so it's a bit early, but I don't want to keep you. I've already kind of been rambling for the last 10 minutes, so I apologize for that. So thank you guys for coming today. Remember, on Monday we don't have any class, and so please don't show up here. I'm not going to be here. I won't be on the Zoom room at all. But I will have office hours on Monday. So Monday 3 to 4. If you have any questions about anything, you can stop by office hours on Zoom and you can talk there. Okay. So hope everyone has a good long weekend. And I will see you guys a week from now on Wednesday for ANSYS Activity 3.
Thank you, Dr. Chan.
Yeah.
Can you go over the hardening?
Oh, sure. Yes. Yeah. So for plastics, so for hardening rules, when you have a plastic material, once you kind of exceed that elastic limit, then the strengths of the materials actually goes up. So that kind of that yield strength goes up. And usually we kind of differentiate between tensile compressive strength. And so there's a couple ways that these strengths can be related. So if you do say kinematic hardening, then the compressive and tensile strengths, the difference between them is going to be the same. And so with kinematic hardening, if one gets stronger, the other one typically gets weaker. But for isotropic hardening, what you assume is basically both are getting stronger at the same rate. And so if one goes up, the other one goes up at the same rate. Yeah.
It's kind of personal one. I wanted to get the finals information and the dates.
Oh, the final?
Yeah.
So there's
So this class and the 417, both of them. Final project.
Yes.
Monday after the week.
correct. Yeah.
And finish the final.
Yeah. Right. So there's no final exam in this class. So it's going to be final project and it's going to be due the Monday after finals week.
Is it going to be an individual thing or like a group thing?
They're all individual.
If I finish early, that's it.
That would be great because then I can start grading early. Yeah.
Thank you.
Yep.
That's my name.
Okay. Yeah. Oh, nice.
So that again.
Oh, yeah.
And here is the last working day for all of us, right?
May 20th?
Yeah, May 20.
I believe so. Yeah, something like that.
Or is that the last submission?
I think that's the last submission day because I think the last lecture, we don't have any lectures during finals week.
Yeah.
So I think the last lecture is probably going to be May.
Friday was the 12th.
Yeah, so it'd be May 10th. The last.
Also, I want to talk about the access class.
Okay. Oh yes, Kevin sent me the forms. Today I was really busy, so I didn't get a chance to sign it. But it is in my inbox. I need to sign it. Okay. Did you guys? I know you asked me over the weekend. Was your professor okay with you staying in the room?
He was for a while, but later it was.
Okay. Yeah. So the reason I said that is because if you guys get in trouble, then
He'll be responsible.
He'll be responsible.
Yeah.
So that's why I don't want to make a decision and then have him live.
So just that weekends are when I'm free, and weekdays I have an on campus.
Yeah.
So it gets a little hard to work on weekdays.
Sure,
That's what
sure. Yeah, let me. I have some more free time tomorrow, so I'll sign the forms and I'll get it back. So you should have access by this week.
Thank
Yeah.
you.
See you Wednesday. Have a good weekend. Emergy, any final questions? Okay. All right. So I'm gonna go sign off. So hope you have a good long weekend and I will see you next Wednesday.